Welcome to Mythosium, the channel where science and imagination meet clarity. Here we explore the mysteries of the universe in a way that makes even the most complex theories feel simple and intuitive. Today we're diving into one of the strangest and most fascinating ideas in modern physics, the possibility that parallel worlds actually exist. It sounds like science fiction, but this isn't about fantasy universes or alternate realities from movies. This idea comes directly from the mathematics of quantum mechanics, one of the most successful theories in science. And when you follow that math to its logical conclusion, it points to a reality much stranger and far more elegant than most people realize. Let's start with the basics. In classical physics, the physics of Newton and Einstein, if you know the position and velocity of a particle, you can calculate exactly what it will do in the future. Everything follows a predictable path governed by equations. The universe, in this view, is deterministic, like a perfect clockwork machine. Quantum mechanics changed all that. In quantum physics, if you know the state of a particle, something described by what's called a wave function, you can use the Schrödinger equation to calculate how that wave function evolves over time. The wave spreads out, representing all the possible places that particle might be found. But here's the problem. When you actually measure the particle, you never find a spread out wave. You find a single point, one specific outcome. So how do we reconcile that with the smooth continuous evolution predicted by the Schrödinger equation? This is the mystery at the heart of quantum mechanics, the problem of measurement. When physicists first encountered this paradox, they assumed the act of measurement was somehow special. After all, measurement produces a real observable result, something definite. So the theory was adapted to include two sets of rules. 1. When no one is measuring, the wave function evolves smoothly under the Schrödinger equation. 2.3. When a measurement occurs, the wave function suddenly collapses, choosing one specific outcome at random. 4. The probability of that outcome is given by the square of the wave function's amplitude, a rule proposed by physicist Max Born in the 1920s. This rule, though incredibly successful in experiments, introduced something unsettling: randomness at the heart of reality. The universe was no longer strictly deterministic. Einstein famously disliked this idea, insisting that God does not play dice. But so far, the mathematics and the experiments have agreed randomness seems built into the very structure of nature. One of the most famous thought experiments that exposes this paradox is Schrödinger's cat. Imagine placing a cat inside a sealed box with a radioactive atom, a detector, and a vial of poison. If the atom decays, the detector triggers and releases the poison, killing the cat. If the atom doesn't decay, the cat survives. According to quantum mechanics, before you open the box, the atom exists in a superposition, both decayed and not decayed at once. And because the detector and cat are connected to that atom, they too become entangled in the superposition. So inside the box, the cat is both alive and dead at the same time, at least according to the equations. Only when you open the box and make a measurement does the wave function collapse, and the cat becomes definitely alive or dead. This seems absurd, and that was Schrödinger's point. He invented this thought experiment not to celebrate quantum mechanics, but to show how bizarre its interpretation really was. But what if there's another way to understand it? One that doesn't require wave function collapse or randomness. Let's take a closer look at three key quantum ideas: superposition, entanglement, and measurement. First, superposition. Quantum objects can exist in multiple states at once, not because they're switching rapidly, but because their wave function describes several possibilities simultaneously. We can actually see this behavior in experiments. For example, in the famous double-slit experiment, when electrons are fired one by one through two slits, the pattern they create on a screen isn't just two bands. It's an interference pattern, as if each electron went through both slits at once. This means the electron's wave function must exist in a superposition. Part of it passes through one slit, part through the other, and the two paths interfere like overlapping ripples on water. So superposition isn't just a theory, it's something we can measure and confirm. Next comes entanglement. Imagine two electrons fired toward each other, bouncing apart after a collision. Before we measure them, their properties, like momentum and spin, exist in superpositions. But once we measure one electron's momentum, we instantly know the others, even if it's light years away. That's because the two electrons don't have independent wave functions anymore. They share a single connected wave function that describes both of them. Measuring one instantly affects the other, not through faster-than-light communication, but because they are parts of the same mathematical object. This is entanglement. And it's not just a quirk of theory, it's been confirmed in countless experiments. So now we arrive at measurement, the most mysterious part. Why should there be one rule for how systems evolve when we're not looking, and another when we are? Is observation really something magical that changes reality? What if measurement isn't special at all? What if we apply the same quantum rules, the Schrödinger equation, to everything, even the measuring device and the observer? Then, instead of a wave function collapse, something else happens. When a quantum system interacts with its environment, the two become entangled. The environment, including air molecules, photons, and the observer, splits into different states, each corresponding to one possible outcome. This process is called decoherence. It doesn't destroy the other possibilities. It simply separates them, making each one effectively isolated. In one branch of reality, the cat is alive. In another, it's dead. Both outcomes happen, but they no longer interact. You, the observer, also become part of this branching. There's now one version of you that sees the cat alive, and another that sees it dead. Each of you experiences a perfectly normal, consistent reality. And that's the many worlds interpretation of quantum mechanics. In this view, the wave function never collapses. It just keeps evolving smoothly, as the equations say it should. Every possible outcome of every quantum event happens, but each in its own, separate branch of the universe. This means that reality constantly splits into countless versions, perhaps infinitely many, as quantum interactions happen all around us. Every photon scattering, every radioactive decay, every random quantum fluctuation leads to more branching. These aren't copies of the universe being created out of nowhere, they're just parts of the same universal wave function, evolving in parallel. They don't require the extra energy or space. They're already built into the mathematics. In fact, from the standpoint of physics, many worlds is the simplest explanation. It requires no special rule for measurement, no mysterious collapse, and no new physics. It just takes quantum mechanics exactly as written seriously. Of course, that raises fascinating questions. How many worlds are there? How often does this branching happen? And is there any way to detect the other worlds? The truth is, we don't know. Every quantum interaction, even the decay of a single atom in your body, could trigger new branches. If that's the case, universes could be splitting around us constantly, countless times every second. Some physicists suspect there could be infinitely many worlds. Others think the number might be finite but unimaginably large, perhaps limited by the total information the universe can hold. What's important is that all these worlds aren't random or chaotic. They're structured, predictable outcomes of quantum laws. The many worlds interpretation doesn't mean everything imaginable happens. It means everything that can happen according to the Schrödinger equation does happen. So, does that mean there's a version of you out there who's a world leader? Or a version who made a completely different choice years ago? Possibly, but not in the dramatic movie sense. Each version of you would be a product of quantum branching, separated forever from the others, each living in its own consistent timeline. From your perspective, you'll only ever experience one reality, the one you're entangled with right now. But from the perspective of the universe's total wave function, all outcomes coexist, evolving side by side. Many scientists still find this idea uncomfortable. After all, it challenges our intuition about reality. It suggests that what we call the universe is just one slice of a vast multiverse, a branching structure where every possible quantum outcome unfolds. But it's also elegant. It restores determinism to physics. It eliminates the arbitrary collapse rule, and it unifies everything, observers, instruments, particles, and light, under one continuous equation. That's what makes it so powerful. At Mythosium, we're not saying this is the final word on quantum mechanics. No one knows for sure whether many worlds truly exist. But if the mathematics of quantum physics is correct, and it has passed every experimental test so far, then the idea of parallel worlds might not be just a theory. It might be reality. And that's perhaps the most astonishing part of all, that the most illogical, elegant version of physics might also be the strangest. So the next time you wonder about alternate realities, remember, the multiverse might not be somewhere else. It might be right here, woven into the fabric of quantum mechanics itself. Thanks for watching. If you enjoyed exploring the science behind parallel worlds and want to uncover more hidden truths of the universe, make sure to subscribe to Mythosium, because here we make sense of the impossible, one idea at a time.